Welcome to the Star Delta transformation. That is the circuits in star connection with 3 resistors here on the left side should behave equally to the delta connection of the resistors on the right side. And how it's usually done is you look into the 3 terminals and write down the resistances, and then you set them equal. If all possible combinations behave equally, left side and right side, then you have found the full transformation. That's because by superposition, all terminals at the same time will then also behave equally. Well, that's the idea behind it. So let's determine the resistances between the 3 terminals while letting one open. So the first pair of resistances is between 1 and 2, and that's step A. And we see a series connection while terminal 3 is open. This resistance between 1 and 2 is R10 plus R20. And then we look here on the right side, we let 3 open, and what we see is a parallel connection of R12 with R13 and R23. If we put it all together, we get this fraction. Here in a denominator, we get the sum of all 3 resistances. That's R12, R23 and R13. And we have a pair combination here within the numerator. It's R12 times R23 and R12 multiplied by R13. That's equation 1. For B, we look into the terminals 2 and 3. And on the left side, we get the equation R20 plus R30 for the star connection. 1 is open. And on the right side, if we put it all together, we get again the same denominator. It's R12 plus R23 plus R13. And the numerator is R13 multiplied by R23 plus R12 R23. That's equation 2. So the final equation, we will have 3 pairs, is between 1 and 3. So this is C. Of course, this is also C. To make it clear here, that's B. And that's, of course, A. Again, the left side is R10 plus R30. And the right side here, our delta, shows an R13 in parallel with the sum of R12 and R23. And if we put it all in one fraction, it's R12 plus R23 plus R13 as the denominator. And the numerator is R13, R12 plus R13, R23. Then we will define the denominator as the sum of R12 plus R23 plus R13. Well, in that way it's easier to calculate. And we start to solve these equations for R10, R20 and R30. So that's how we will derive the star equations. And that's done by solving these equations for R10, R20 and R30. Actually, it's not that difficult. I have plenty of examples on the net, so I can make it short here. For R10, you simply calculate equation 1 minus equation 2 plus equation 3, and then you get for the left side R10 plus R20 minus R20 minus R30 plus R10 plus R30, and then equals to, so we pull out the common denominator. It's 1 divided by the sum of R, and then we can just use those numerators, and that's then rather simple. So it's then R12, R23 plus R12, R13 minus R23, R13 minus R12, R12, R23 plus R13, R12 plus R13, R23. So hope I did it correctly. So it's R12, R23, R12, R13 minus R13, R23 minus R12, 23, 13, 12, 13, 20. That's correct. Okay. Let's see if terms cancel out, and they will. So R30 here and here, and we have R20 and R20. So what's left is 2 R20, and on the right side we have R23, R13. That's equal to this, so this cancels out, and this minus term 12, 23, 12, 23. So we have 2 times R12, R13 here and here. So here and also 2 times. So you divide by 2, and what you get then is R10 is equal to R12, R13. Yeah, and the sum of R, we can resubstitute the sum of R with equation 4. You may write, of course, the sum of R, but you can also write R12 plus R23 plus R13. So I'm sure you have seen those equations, and it's rather simple how to derive them. Just to make a shortcut to the other 2 equations. So that's equation 5, and that's 6 then. For R20, you simply calculate equation 1 plus 2 minus 3, and what you come out with is R20 equals to R12, R23 divided by the sum of those 3 resistances of the delta resistances, and that's equation 7, the second transformation equation. And the last is 3. We solve those 3 equations for R30. To obtain R30, you calculate minus equation 1 plus equation 2 plus equation 3. And if you put it all together, you get for R30, that's R13, R23 divided by R12 plus R23 plus R13. Well, I think that's pretty clear, and that's not so difficult after all. If you have ever wondered, why is it so different if you calculate for not the star resistances, but the delta resistances? If you want the same structure for those equations, you have to use the duality of electric circuits. You start inverting the structure and the values. Instead of resistances, you use conductances. And of course, I explained that for deriving R10 and so forth, we used the reduction of a 3-terminal circuit to a 2-terminal circuit at no load. What's the exact opposite of that? That's the reduction of a 3-terminal circuit to a 2-terminal circuit at short circuit. And that's the whole point. So let's see with what type of equations we come up with this thought. We short circuit 2 and 3. And what we have here is, so the conductances between 1 and short circuited 2 and 3 with short circuit between 2 and 3. So we see those 2 conductances are in parallel, but if you write that down as conductances, you can simply add them. So it's G12 plus G13. And then we look here on the right side. And of course we have the short circuit also for A, 2 and 3. And again from 0 to short circuited 2 and 3, G20 and G30 are in parallel. You can simply add them up. That's G20 plus G30. And in series with this sum of these 2 conductances is G10. So I have a special sign here to make that clear, because I cannot write a plus here even though they are in series. but the calculation rule is not adding them up. So next step is putting it into a fraction, and that's G10, G20 plus G30 divided by G10 plus G20 plus G30. And if we multiply all those terms, we come out with the final fraction, and that's G10, G20 plus G10, G30 divided by the sum of all three conductances from the star. And that's equation 9. So the same thing we'll do for short-circuiting 1 and 3. We determine the conductances between short-circuited 2 and 3 and short-circuited 1 and 3. With the short circuit between 1 and 3. What we get is G12 plus G23, and that equals to, same here, short circuit between 1 and 3. Same thing, so G20 in series to the parallel conductances, it's G10 plus G30. And if we put it all together, again we have the same denominator, it's G10 plus G20 plus G30. And the numerator is G10, G20 plus G20, G30. And that's equation 10. So the final one is we put a short circuit between 1 and 2. That's C. That's also C. And for C, the conductance is between 3 and short-circuited 1 and 2, with short circuit between 1 and 2. And we get G13 plus G23. And that equals to, here's G30 connected in series to the paralleled conductances G10 and G20. And that leads us to this fraction. Again, we have the sum of all three star conductances. And the numerator is then G10, G30 plus G20, G30. And that's equation 11. So as you probably have noticed, now we have the same structure as we had in the previous delta to star transformation. So you may already sense that it'll be rather easy now to obtain the equations for solving those equations for G12, G23 and G13. So again, we can use the sum of those three conductances and define them as the sum of G, and that's G10 plus G20 plus G30, and that's equation 12. So let's derive now those delta conductances from the star conductances. In other words, that's solving for G12, G23 and G13. Solving for G12. In order to do that, we will add equation 9 with equation 10 minus equation 11. And what we get is G12 plus G13 plus G12 plus G23 minus G13 minus G23. That equals to 1 divided by the sum of G. And let's open the parentheses. It's G10, G20 plus G10, G30 plus G10, G20 plus G20, G30 minus G10, G30 minus G20, G30. And now let's see if any of those terms will cancel out. Yes, they will. So we have G13 cancels out with G13. we have minus G23. It cancels out with G23. So let's look at the right side. G10, G30 cancels out here, and G20, G30 cancels out here. So we have 2 times G12 on the left side, and we have 2 times G10, G20. So it's the same structure as we had with those star resistances. Now we have delta conductances. So we get out with G12 equals to the common denominator is G10 plus G20 plus G30, and that's G10, G20. And that's equation 14. Well, as you can imagine, we do the same thing now for G23 and G13. We can take a shortcut here. So for the second equation, that's for G23, we calculate minus 9 plus 10 plus 11. And what we get is G23 equals to G20, G30 divided by the sum of all those 3 conductances. And that's 15. The last equation is solving for G13. And that is equation 9 minus 10 plus 11, and we get G13 equals to G10, G30 divided by G10 plus G20 plus G30, and that's 16. And that's it. And you see the same structure in the equation. It's just now made up of conductances instead of resistances. Final question. I want the equations with the resistances in them. I don't like those with the conductances. Well, first of all, it's not really a difference if you use those resistances. I think that's number 4. I hope it's right. So page 5. Well, let's take 14 and invert the equation. Let's find the reciprocal of that. So let's take the 14. It's here. Oh no, that's still plus, of course. It's 14 to the power of minus 1. And what we have then is 1 divided by G12 equals to the sum of those 3 star conductances. And the denominator is then G10 times G20. That's 17. So 1 divided by G12 is of course R12, and G10 divided is R10, and 1 divided by G20 is of course R20. And we leave the sum in those parentheses, and that's still G10 plus G20 plus G30, equation 18. And now we multiply those resistances by the conductances, and we have R12 equals to R10, R20 times G10, but G10 is 1 divided by R10. So plus, same here, it's R10, R20 times G20, and G20 is 1 divided by R20 plus R10, R20 divided by R30. So what we have here, this cancels out, and this is equation 19. And our last equation is of course R20 plus R10 plus R10, R20 divided by R30. That's our final equation. So hope you enjoyed it. See you next time.